All right. I'd like to talk about a little bit about digital theory here, a little bit about levels in the DSP, and like I say, a little bit of basic digital theory. And yeah, let's start with a very simple converter. Um, i- if we had just 4 bits to work with, then as we've if you look at my other videos here, when I do a lot with 4 bits, that's just 16 different values. So I'm just gonna not try to do this in. I suppose I can do this two's complement. Why not? So we got zeros in the middle, and then 0, 0, 1, 0, 0, 1, 0. That's 2, 1, 1. It's 3, etc. All the way up to 1, 1, 1, 1. I'm sorry, 0, 1, 1, 1, 1, which is a 7. So we're going from 0 to 7 in the positive side. And then the negative side, of course, is 1 minus is 1, 1, 1, 1, and 1, 1, 1, 0, and 1, 1, 0, 1, and etc. down. Uh, so, this is plus 1, this is minus 1, plus 2, minus 2, etc. down until we get a 1. I'm sorry, put 1 in the right place. 0, 0, 0. And so this is a minus 8. Um, and so we have 16 different values because we have 0 as one of the values. And so, yeah, so this is all the values we have. We have 4 bits. That's all we have to work with. And so if I were to draw this out, and again, I'm going dot, dot, dot here, there, as levels in, I'm not going to do this perfect here because it's not, doesn't need to get perfect, dot, 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 and then the max. And we're going to try to sample a sine wave. And so we're going to draw a sine wave in here, right? And that's fine. And so at any particular instant, now we have time. So we're going to have a certain sample rate that we're going to see, oh, this is at a 2. So at this particular moment, this is going to be the sample. Okay, the next moment, the sample is going to be here. The next moment, the sample is going to be there. And we're going to quantize and give it a value based on these 4 bits we have to work with, or 16 values. And it's going to go, if it happened to be right there, it'd be right at 0, and then, minus whatever, minus 2, or whatever this happens to be, and et cetera, et cetera. Away we go. And we have, and that's how we sample audio. Now, what I'm wanting to talk about here is what happens when we run out. Like, how much level can we get? So if we come all the way up really close and we sample this, we can, give it the value 0, 1, 2, 3, 4, 5, 6, 7, and then we just made it down, so we're good. And if we get down to minus 8, we can give it a minus 8. But what happens if the sine wave really wanted to go here? And likewise in the bottom. Am I still on the screen here? Yeah, barely. Um, Well, what happens is we're going to give it a number, and then when we get to 7, we're going to give it a 7 because there are no more numbers. We have no more bits. We've run out of bits. That's it. We have the max number. It's pegged. It's clipped, and likewise in the bottom, it'll clip at a minus 7, and that's what clipping is all about. But the maximum number we can ever get is the amount of data. So we have 4 bits. So um, yeah. No, I don't want to go there right now. So we only have 16 values, and so there's going to be a lot of quantization error and stuff like that. But the amount of level, okay, so we can only do so loud of a signal with 4 bits. Now, if I were to add one more bit and end up with, one more bit I can add, then that would double the amount of voltage I could show because it's not just one more value. It's, remember, we're going to go with 0, 0, 0, and then 1, 0, 0, 1, and 1010, and go on and on. So we're going to double the amount of values by just adding one bit. And so we can double the voltage that we could sample. And if you remember new digital theory, if you've ever studied digital theory a little further, when you double the voltage in dB, when you look at the dB formula, it's relative to there's a reference voltage and there's a relative to a reference voltage to get X amount of dB. So when you double the voltage from the reference, you're adding um, 6.021 dB, I believe it is, for every doubling of voltage. So every time you double the voltage, you're adding a little bit more than 6 dB. We just, fudge it. We don't need to be that perfect. And we just say, okay, you double in voltage, you add 6 dB. So plus 6 dB for every doubling of voltage or every halving of voltage. So divide it by 2, you're going to lose 6 dB and minus 6 dB. So therefore, the amount of range of the quietest signal to the loudest signal we're going to be able to get with a 4-bit number is 4 times 6. So that's 24. So 24 dB, that's all we're going to get. If we get an 8-bit, so let me start writing this down. Um, yeah, so if we have 4 bits, right, it's going to be 24 dB of maximum signal to noise or dynamic range. Actually, DNR is what we're talking about, dynamic range. Um, and if it's 8 bits, it's going to be 48 dB. Because what we're doing for the math here is 8 times 6 is 48. Like I said, it's 6.021 or whatever the number is, but close enough, 48 dB. So if we go 16 bits, this you guys might know about, you get the theoretical signal to noise is 96 dB. That's the most you're ever going to be able to get out of a 16-bit PCM data. Um, you won't get a converter that's better than 16 bits because it's impossible. Um, because that's all the numbers you have. So if we go to 24 bits, we're going to get 144 dB. So that's the maximum we're going to get with 24 bits. That's usually a number I have very well memorized. Um, 32 bits, we're going to be 192 dB. Signal, DNR, dynamic range. A theoretical dynamic range. Now, 24-bit converters, you're not going to find one that's 144. Yeah, it might be 122 or something like that. That's where you get the EOB, effective bits, and it might be a 22-bit converter or 23-bit converter because there's noise. That when you look at the signal to noise ratio of the converter, it might not. A 24-bit converter, chances are, it won't do a full 24 bits of resolution. But it gives you an idea. So the concept here is the doubling. Every bit you add 6 dB. Another bit you add 6 dB. Another bit you add 6 dB of DNR. So that's the important little details to kind of know here. Okay, so back to this sampling with every bit being a different level that you can get a different number out of, and then like I said, the maximum number, however many bits, you can't get any higher. There's no numbers there to represent the level greater than the number of bits you have. So if this was 24 bits, and we have quite a few numbers here because it's 2 to the 23. So we have quite a few different numbers in there. Um, but we have 24 bits worth of numbers. Um, but as soon as you hit the max, you've hit the max. There's no more numbers to represent it. So therefore, a maximum level, this is where you get the, uh, 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 the digital dB scales. So the maximum we're going to call 0 dB the max FS, full scale. It's a capital FS. It doesn't, it's not a small FS. You generally think of frequency of sampling, so sampling frequency. But capital FS, it's full scale. So a 0 dBFS signal is going to go right to the very last number and right to the very bottom number, and it's going to be exactly using all the numbers available to it and every range in between, every single number. It's using every single bit. Um, that's a 0 dBFS signal. For 24 bits, it's going to be, X amount of values. So there's no going over it. It's impossible. There's no numbers to go. You can't go any higher. Now, we do this in the DSP kind of all the time. We kind of um, break the math, break the physics here, because we bring in a 0 dBFS signal and then we add gain to it. Huh? Well, if you remember when I talked about the number formats, we we did the trick with bringing in the data into the core. So we take the 1.23 number, which is a which is a 24-bit number, and then we bring that into the core. And in the case, let me just talk about the Sigma 300. In the case of the Sigma 300, we translate this, we add 7 bits to the top, and we add 1 bit to the bottom. So we end up with an 8.24. So now, this 1.23 maximum sine wave is only going to 1.23 here. There's 7 more bits than there are here. So we can boost 7 more bits. How many dB per bit? Again, 6 dB per bit. So if we can use 7 more bits, so that 7 times 6 is 42 dB. So we have 42 dB of headroom. We can boost by 42 dB and still not clip if we had an exactly 0 dBFS signal. So we can go higher than 0 dBFS of a 24-bit signal because we're going into the core, we're giving it more bits. But then when you're going back out of the core, you got a problem because you don't have bits to represent it. And that's what we talked about, the saturation and that sort of stuff. So you have to, if you gain up the signal in the DSP core, you have to remember to compress it or bring the volume down or do something to bring it back down within the confines of a 24-bit number. Otherwise, when you put it out of the core into the serial port, out of the actual DSP, you're going to get a clipped signal because you've run out of numbers. We have 32 bits in the core, but we only have 24 bits we're sending out. So you have to be aware of this a little bit. But we have quite a bit of gain because we have 7 bits. In the Sigma 100, we're going from a 1.23 to a 5.23. So we're adding 4 more bits. And so 4 times 6 equals 24 dB. So we can add 24 dB to the audio signal coming into the Sigma 100 cores. So the ADAU 1701 stuff, you can add 24 bits, up to 24 bits, and you're good. What's handy to know is in the objects. When you're in Sigma Studio and you drop in an oscillator, an X frequency, you drop in an oscillator, and that's your signal source. That oscillator is exactly 0 dB FS 24 bits. It's not, let's start on a Sigma 300 core. It's not 0 dB FS of an 8.24. It's a 1.24 in the case of the Sigma 300, and a Sigma 100 is a 1.23. But you can still think of it as a 24-bit number. We got 1 extra bit to deal with in the bottom side here, which it gets truncated. It's still going to be a 24-bit oscillator. But that's very important to know that the oscillators in Sigma DSP in the core, when you drop it in, the programmed oscillators are exactly a 0 dBFS for a 24-bit signal. So if you take that output of the oscillator and put it out the serial port, it won't clip. It'll be exactly 24 bits. And truncating this bottom bit isn't the clipping. You just lose one bit of noise, which is fine. Um, and so yeah, so you end up with exactly the right level, which is great to know because you can take this and put it out of, output one or output two or whatever, take the oscillator and send it directly out. And you can test your serial ports. You can test your DACs. You know that the DAC will be that's the maximum level of the DAC. The DAC should not clip, and the DAC built into the 1701 won't clip. That'll be exactly at its maximum. Um, you can see how much level is it. And so obviously it won't get any louder than that. And the serial port, you can check your communications settings to make sure all your bits and your left justified and right justified and all the fun stuff of rising and falling edges are all set properly to properly transmit. Because you can then go to another DSP or something else and see what the level is. And it should be exactly a full scale level. If it's 6 dB down, that means the data is coming in shifted to the right by 1 bit. You lost 6 dB. If it's clipped, that means it got shifted to the left 1 dB by 1 bit, and you end up with a clipped signal. So you your your these oscillators are a great way for you to test your interconnection between parts, between converters, ADCs, DACs, that sort of stuff, or one DSP to another DSP. It's a great, handy little thing to do. Um, and yeah, I think that's it. It's a short little video. Don't forget to hit like and don't forget to hit the subscribe button. Thank you very much.